Hi, welcome to my talk. I'll be presenting SymQEMU, a tool for compilation-based symbolic execution of binaries. My name is Sebastian Pöppler, and this is joint work with Aurélien Francillon. First, let me talk about why we built SymQEMU. What we wanted first and foremost is a tool for fast and flexible binary-only symbolic execution. In previous work, we've shown that compilation-based symbolic execution yields large performance improvements over existing approaches, so we wanted to apply a similar technique to binaries. Why would you want to analyze code without sources in the first place? One possible scenario is you may have proprietary dependencies where source code is not available, or maybe you want to perform security audits like firmware analysis. Lastly, some projects are just too complex and have too many different programming languages for source-based tools to work with. And lastly, why didn't we use one of the existing implementations of binary-only symbolic execution? There are many implementations and they each have their respective strengths and weaknesses, but it turned out that none of them fulfills our particular requirements. Specifically, many focus either on performance or on flexibility, but often you have to choose between the two. And they tend to be very complex, so that building new analyses on top of them is challenging. Let's look at a few existing implementations. The first is QSYM, a relatively recent binary-only symbolic executor, which is very fast. So the idea here is that during execution of the target program, QSYM performs dynamic binary instrumentation and inserts new instructions into the program that handle symbolically all the computations that happen. This means that the symbolic semantics are implemented at the level of x86 machine code. The resulting system is very fast and it is conceptually simple, which is a good thing. It's easy to understand and extend, but it is tied very strongly to the x86 architecture. Because implementation of the symbolic semantics happens at the level of machine code, QSYM has to handle each and every x86 instruction that could reasonably appear in a target program. This means that porting QSYM to a different architecture is challenging, and also it can only analyze binaries for the architecture that it runs on. Next, let's look at Anger, which is sort of the opposite of QSYM in the dimensions that we are interested in. It is very flexible, yet its performance is lower. How does it work? Anger takes a binary and translates it to an intermediate representation called vex, and then interprets the instructions symbolically. For performance reasons, there's also a fast path that executes the instructions that do not require symbolic execution in the Unicorn CPU emulator, which is based on QEMU's CPU emulation. As a result, Anger is very flexible. This is something that it largely inherits from VEX, which supports a number of different architectures, but its performance is relatively low because it is geared at interactive exploration and scripting. Part of the reason for the low execution speed is the Python implementation, which is a technicality that could be changed. But there's also the more conceptual reason that in the end, symbolic execution in Anger is based on interpretation, which is slower than running compiled code. Lastly, I would like to discuss S2E. S2E is a very flexible whole operating system symbolic executor. The way it works is basically it combines QEMU and CLI. CLI is a well-known tool for source-based symbolic execution. And the combination is achieved by first translating a binary to QEMU's internal representation called TCG-ops, and then performing another translation to LLVM bitcode so that the program can be fed into CLI for symbolic execution and in particular interpretation. Now, this double translation is not strictly necessary, and I understand the S2E developers are working on removing it. What's also interesting to note is that S2E runs an entire operating system, so you have full visibility into the kernel and everything that goes on in the system, but it requires more work to set up. Conceptually, this is a very flexible design, but so far it's been implemented only for x86, and it appears to be very difficult to port it to other architectures because of the many different components involved. So in summary, S2E is very flexible, but it is highly complex as well. So let's discuss the goals for SymQEMU. As I told you before, we wanted a fast system and we wanted it to be architecturally flexible. And let's be a bit more precise about what this means. It's two things really. One is we wanted support for a number of different target architectures so that we can, for example, analyze the firmware of our router. And we would like to run the analysis on an architecture that is different from the binaries target architecture, so that in the case of the router, you don't have to run the analysis on the router. Third, we wanted a robust system. We wanted to build upon parts that already exist and that are well tested, in particular for architecture emulation. And lastly, we wanted to build a simple system, which is to say a system that people can easily understand and build upon. The resulting design compares two things: QEMU for emulation and compilation-based symbolic execution to achieve high performance in symbolic execution. And the idea is that during the binary translation phase in QEMU, we insert new instructions that implement symbolic handling. So let me show you the design. Here you see unmodified QEMU. It takes a binary, translates it to the intermediate representation, TCG ops, and then translates that representation to machine code for your host CPU. SymQEMU just inserts one more step in the pipeline. After the binary has been translated to TCG ops, we insert additional instructions that symbolically handle each operation that happens in the program. And then we pass the result back to QEMU for regular translation to host machine code. So our inserted instructions end up being compiled into the dynamically translated binary. The result is a relatively simple implementation, around 2,000 lines of C code for this additional step in the pipeline. And we implement symbolic semantics at the level of TCG ops. This makes for a conceptually simple system as well, because there are just around 20 instructions in this intermediate representation. Moreover, for symbolic reasoning, that is to say all the interactions with the SMT solver, we just reuse the backend from SymCC, which is in turn based on QSYM. The resulting system is very flexible architecturally, which is a property that we just inherit from QEMU. In particular, it fulfills the two criteria that we support a number of different architectures, and the target architecture doesn't have to be the same as the analysis architecture. We were able, as a proof of concept, to add support for ARM64 with just 17 lines of code. And the resulting system is very fast, which I'm going to show you next. For the evaluation, we performed 3 sets of experiments. We ran SymQEMU in Google Fastbench, we performed whole program analysis, and we ran a benchmark comparison. In the interest of time, I will just summarize the results of Fastbench and focus on the other two. So Google Fastbench is an evaluation service for fuzzers. It tests them on open source targets. And at the time when we used it, it had support for 12 fuzzers on 21 targets. The experiments are performed by Google and you receive a detailed report. The one for SymQEMU you can access at the URL shown below. We integrated SymQEMU by performing hybrid fuzzing with AFL. In particular, we ran one AFL and one SymQEMU process and made the two exchange new program inputs. This is the same setup as we used for SymCC and as the QSYM authors used in their evaluation. In total, SymQEMU achieved the second highest score. without using source code. Many of the fuzzers in that comparison have access to source code and make use of it. It outperformed all other fuzzers on 3 out of the 21 targets, and it was better than pure AFL on 14. Next, let's look at the whole program analysis. Here we picked 3 open source targets, the same as we used in the SymCC evaluation for comparability. And we picked 1 closed source program to also show how SymQEMU is able to analyze binary-only programs. We compared SymQEMU with QSYM and SymCC on the open source targets only in the case of SymCC, performing hybrid fuzzing with AFL as I just described. We compared it with S2E, performing symbolic exploration with the default search strategy. And we compared with pure AFL. In each of those cases, we used 3 CPU cores. We ran the experiments on modern hardware, and we had 2 GB of RAM available per core. The paper has some details on the S2E setup that are not essential here. And we analyzed each program for 24 hours, performing 30 iterations for statistical significance. Here you see coverage over time for the 3 open source programs, and you can see that SymQEMU, the purple line, achieves highest coverage in each of those cases compared to the tools that are able to handle binaries. In comparison with SymCC, it is better sometimes, a little worse sometimes, but the interesting thing is that SymCC requires access to source code, while SymQEMU does not. We see a similar picture on the closed source RA program. So in summary, we see that SymQEMU significantly outperforms QSYM, S2E, and pure AFL, and it achieves performance that is comparable with SymCC but doesn't need source code for it. Next, or last, we look at the benchmark experiments, and here the goal was to analyze the performance differences in a more controlled environment. Specifically, we performed concolic execution on a fixed set of paths through the programs, and we chose the 3 open source programs from our whole program analysis setup, where after the whole program analysis we picked 1,000 randomly selected test cases for each of the programs. We ran them in SymQEMU, QSYM, and SymCC, and we measured the time spent in execution and SMT solving. In the results, you can see the split between green and purple, solving and execution, for each target and each symbolic execution tool, normalized to the execution time of the slowest so that we can see the difference in absolute execution times. Now, the interesting result here is that SymQEMU executes faster than QSYM indeed, and it is closer to SymCC in execution, even though it doesn't have access to source code. An interesting side note is that SymCC's queries seem to be easier than those of the other 2 tools, and I refer to the paper for a discussion of that aspect. In summary, we've shown that compilation-based symbolic execution is applicable to binaries and yields a very flexible and fast system. SymQEMU is available online, and on the website you'll also find details for our evaluation. Thank you.